All right, thank you everyone for being back. The poster session is still ending. There is a lot of passionate discussions and passionate presentations. So they will be here eventually. There are about 50 students still presenting posters. But in the meantime, we do have to get started because our schedule is also tight. So our next speaker is our own Christiane Jablonowski. So she's a professor in the Department of Climate and Space Sciences at the University of Michigan, where she also received her PhD back in 2004. And after that, she was a postdoctoral scientist at NCAR and also a visiting scientist at NOAA, so Geophysical Fluid Dynamics Laboratory, and also worked as a consultant in the European Center for Medium Range Weather Forecast, which is very well known as the ECMWF in the UK. So Christiane's research portfolio includes atmospheric fluid dynamics, weather and climate modeling, including high-resolution modeling, tropical dynamics, model hierarchies and coupling techniques, numerical methods, scientific computing, and more recently, machine learning techniques for climate sciences. So she works with the weather and climate models from NOAA, the Department of Energy, and NCAR. She was the recipient of the DOE Early Career Award in 2010, which I happened to notice when I was looking for faculty positions back in the day, and the PCASE Award. So she currently heads the steering committee for NCAR's Community Earth System Model, CESM, and is a co-lead for NOAA's short-range weather prediction model. In short, she does awesome work, and she has a very impactful role in climate models in the country and beyond. So very happy to have you here. And looking forward to your talk.
Thank you. Thanks for coming. Let me see. This is hooked up. Thanks for coming. Yeah, this is a wild ride. It's only a 25-minute talk, a wild ride through weather and climate modeling. And I know this is a broad audience. It's a general audience talk. And I hope I can kind of take you along this ride, and I called it the computational frontiers in weather and climate modeling. I present a little bit of my own work, but also just where the field of weather and climate modeling stands in when you think about high-performance computing and where the emerging frontier is in terms of exascale computing. All right, let me give you a quick overview of what I'm talking about. So I start with a super brief introduction, what climate modeling is all about. Then I'm showing you some emerging frontiers. These are high-resolution, kilometer-scale resolutions that we are currently approaching in the climate and weather modeling world. I point out the HPC strategies and hurdles, the challenges that we are facing. Talk about digital twins, which is a concept that also pops up in other engineering sciences, also in the climate sciences, and you will kind of learn how confusing this word even is, and then I just point out a couple of things where the field is going. All right, okay, this is my quick introduction to weather and climate modeling. I'm not certain whether people are familiar with that. Let me see whether the pointer works, yeah. So I want to point out two things. We have typically a grid, so this is of course the Earth as you see it. Here you see a latitude-longitude grid on top. We also have a vertical grid. But think about a 3D grid on top of the surface of the sphere. Typically, it's a perfect sphere, which even is an approximation, as you might know. The Earth isn't actually a sphere. It's a little bit ellipse shape. But that's not the topic of today's talk. What I want to point out is that on this grid, you solve partial differential equations, and we actually call it the dynamical core. Think of this as Navier-Stokes equations, momentum equations, thermodynamic equation, an ideal gas law, and mass continuity equation, and moisture. Okay, so these are really just a handful of equations, and we do solve them. We call this the resolved fluid flow, and you see we probably have, horizontal, you kind of see it here a little better, horizontal gradients we can assess. We have vertical gradients. And in the vertical, we are facing some challenges. And what I mean by that, a lot of vertical processes are really small, and that's not just in the vertical, but I'm particularly thinking about clouds or radiation, precipitation. Those processes are super small. They happen at a millimeter scale or maybe a meter scale when you think about turbulence. I want to say this because this grid spacing that you see in the horizontal is typically 100 kilometers. There's basically no way you can compute a cloud or represent a cloud which is maybe just 100 meters or 1 kilometer wide. What we are doing in climate modeling and also in weather modeling, we are then using physical parameterizations, and this is here the box basically. We are parameterizing everything we cannot resolve in a kind of estimated fashion. But that's how, as good as it gets. Yeah? So there's, of course, a lot of uncertainty in the way we do the clouds or we do the interaction. But both together are the atmospheric model. You can basically even use this now to do a weather prediction, a short-term weather prediction. Maybe you need a little bit of land information as well. But the big take-home message, and that's my kind of last word on this, you have basically a fluid dynamics component, dynamical core, and you have physics. Both together make the atmospheric component of a weather and climate model. All right. This is good enough for weather prediction, but not for climate prediction. And what I mean by that, in climate prediction, you're typically after long, long time scales, not just a day or two. So we are typically looking maybe at a year, a decade, 100 years. And over those time scales, weather isn't important. It's actually the boundary conditions coming from the land, the ocean, the solid earth even, that really determine the fate of the climate system. And in order to do this right, in order to have climate predictions do the right thing, we need to have all these other components attached to the atmosphere. And I even here, what I point here in the middle is actually maybe even a data analysis platform, a machine learning platform, or what you have. So when you take a look, atmosphere, water and ice, I mean ocean and ice, solid earth, these could be volcanic eruptions, land and life, this is the land vegetation even that you might have interactive in your model. We have people that impact climate, for example, through greenhouse gas emissions, and we have space parameters, for example, the solar constant or varying space parameters, the input, output, or the interchanges with space. Mostly it's a solar constant that I'm referring to. But what I want to just get home here, in climate prediction, let me kind of take a look here at the upper row. Weather predictions only need atmosphere, land, and maybe some prescribed ocean temperature. That's not true for climate predictions. In climate predictions, you need all the other components active and mean predictive. So that's a big, big hurdle. And you also need to glue these together. They all work on different timescales. So what I want to just get across, it's complicated. Yeah? So I hope you kind of got that out of this slide. All right. Okay, and then you can ask many questions. Once you have a climate model or a weather model, you can ask many questions. If somebody gave you a bigger computer, what do you want to do with that? Well, you can come up with various answers. For example, you can say, hey, let's crank up resolution to finer and finer grid spacings. That's one way of consuming more compute power. We could maybe go after more complexity, maybe add another component, for example, a chemistry model to the existing system. We could also increase ensemble sizes. A single simulation isn't actually telling you a lot. So we often want some uncertainty estimates. We want maybe different initial conditions, different boundary conditions, and get a feel for the uncertainty. And that points into the direction of more ensembles. Or you can also spend more time on data assimilation, getting better data into your system. So these are basic decisions. Today's decision in this talk is one. And I'm hitting home on the resolution. So if we have bigger and bigger computers, what could we do in terms of resolution? Let's kind of see. Okay, and this is a diagram that points, this is a little bit of jargon, but let me just point you to some of the basics. So we have some basically characteristics length scales for atmospheric motions down here. And this is a logarithmic scale, as you see, and we have some time scales. This is also logarithmic. And what we are typically doing is actually 100 kilometers. 100 kilometers would sit here. And when you kind of look at this diagram, everything bigger than 100 kilometers you can represent, but everything finer you cannot. What is the big dream currently in terms of weather climate modeling? The big dream is actually not to go to 100, but go to 1. That's where the frontier sits. And when I say 1, I mean maybe 1 to 3. Yeah, it doesn't need to be 1, but this is a resolution where you capture or try to capture some cloud systems, bigger convective systems. These are the big thunderstorm systems. For example, in the Great Plains, we have these so-called mesoscale convective systems, MCSs. These are hundreds of kilometers wide, and then you get a chance with like a 1 to 3 kilometers length scale to kind of capture their dynamics. So that's where the dream is. And then basically it means everything beyond this red box is resolvable, starting with these thunderstorm clusters. All right, and where are we with this dream in the community, right? Here I'm grabbing, this is now an animation. It's only a 24-hour animation, but I think it shows a couple of nice details. This is now something at the leading edge of climate modeling. So this is now an animation. This is not from me, but it's coming from the Department of Energy, and this is flickering because it kind of turns over every 24 hours. What you're seeing here is outgoing long-wave radiation. So basically what a satellite would see, a satellite that looks at the Earth. And you can basically, in these patches, you can kind of identify cloud systems. Yeah? So maybe there's even a tropical cyclone sitting here. And then poofy cloud systems here in the tropics and more organized ones here in the mid-latitudes. And this is a very, very fine scale animation. What I mean by that, the simulation behind it was actually a 3 kilometer, was done with a 3 kilometer grid spacing. That's really kind of pushing the edge. Yeah? And that's something that followed a protocol, which I hit on in a minute, which is called DYAMOND. So this is kind of an international protocol, how to compare the leading edge of climate and weather models. And here's one depiction of it. This is when you kind of want to see more, there's here more hidden here under this link. All right. That's where the emerging frontier is. And let me also convince you one more time, this is now a different model. This is the NASA model. It's called GEOS-5. This is also a climate model. This is a few years older than the current simulation, but here my simulation will run at 7 kilometer grid spacing. So a little coarser, but still very fine. And this is an animation. Let me just get started on this. An animation of basically also satellite. It mimics a satellite image. Basically, we are seeing a loop here of clouds. These are simulated clouds, but they do look really like a satellite image. So again, with a 7 kilometer mesh, we can do amazing things. Yeah, we can basically, mimic the system Earth, at least in an eyeball norm, really well. Okay. This motivated, and this is now the DYAMOND protocol, this motivated an international model intercomparison project. This what was called DYAMOND. What was it? So it was basically the international community of weather and climate modelers got together. They all calibrated and configured their models with 3 to 9 kilometer grid spacings, and they all ran a 40-day time period in 2016 or so with real initial data. Not that this is a prediction. I wouldn't say that. A real weather prediction needs a little bit more effort, but it at least has an equal playing field. All models were basically using identical initial conditions, identical setups. And here is a snapshot of these models and one satellite image. And now you can have your educated guess, what is a model and what is a satellite image? There's one satellite image. Let me see whether I have a volunteer that wants to try and guess.
The last one is a satellite image.
This one?
Yeah.
No. No. So, no, they all look alike. No, it's not. It's actually this one. And you wouldn't have guessed this because it's impossible to guess this. So this is actually, I guess some people called it the Turing test, or this is actually an eyeball norm test. Could you tell a satellite image and those simulations apart? And the answer is no. Yeah, so they do look alike. I'm not saying all are accurate from a prediction perspective. They are not. So I just want to kind of get the word out that these models are at a stage where they do amazing things. Yeah, we are not quite, of course, maybe from an accuracy perspective, not quite at the point where we want to be. So I'm not claiming they are all accurate weather predictions. This is a satellite image. This is actually a developing cyclone. A lot of models have that cloud cluster, not all. This is actually 3 days into the simulation. So there's a chance 3 days is a predictive, in the predictive time frame. So there's a chance we even get an okay image or an okay simulation of that tropical cyclone. Yeah, it's kind of amazing how well these models do. And that's where the leading edge sits. All right. okay, how do we get there in terms of computational science? What do we need to do? Before you actually go there, maybe one more thing. And this is now kind of advertisement for our own work here at the University of Michigan. So in our group, we have been doing variable resolution modeling. So it's not just a global resolution you can entertain. You could also entertain the idea of just doing refinements or high resolution in local spaces. And that's also a valid approach. Here you see one approach. This is now with the NCAR community atmosphere model. Here it's 13 kilometers, we have 100 kilometers, and you can really, if you even zoom in, you can kind of see this rather smooth stretching area, yeah, where we are diving here into fine resolution. So that's a perfectly fine approach. The other approach we had been working on a few years ago is adaptive mesh refinement, and that's a kind of a newer, maybe more experimental way of looking at high resolution. And when I start this is a simulation. Let me see where my mouse is. Then here it is. Then you kind of see merging vortices. These are basically vorticity patches, rotation basically. And they are tracked by a high resolution mesh. There are more grid points even in these boxes. This is a Chombo. Maybe people have heard about Chombo. It's an adaptive mesh library from DOE. So this is using their technology. And we are tracing here vorticity as these two vortices merge. All right. Okay. Right, how are we getting to that dream? A dream is a scientific dream of doing 1, 2, 3 kilometer resolution. I'm using DOE here as an example because they are really the leading agency that pushes the frontier. And the pushing the frontier is also related to even this newest hardware architectures that they have at hand. This is a frontier system. It's not even released to the public. So what I'm showing you here are partly their own private allocations, 10 days of frontier that they got before the public gets access. So let me just get you a couple of these performance boundaries or the performance edges that we want to reach. All right, before I do that, okay, let's go over the programming languages a little bit. This is historic. Fortran was used historically for weather and climate modeling, and now we see in the DOE model, we see actually C++ coming. We have various programming models, MPI, OpenMP. This was a classical one, of course, for CPUs. We have OpenMP, MPI, and OpenACC. This is for the GPU attachments of some of the machines. For the Fortran implementation. And the newest kid on the block is MPI and Cocos. And Cocos is a library that gives performance portability. So this is basically now hardware agnostic. And you can have NVIDIA GPUs or AMD GPUs or whatever GPUs under it. And this will do the right performance or the right optimization for the hardware architectures. And Cocos, this is a DOE product, is really tailoring your code to CUDA or can tailor it to CUDA or any of these programming models depending on your hardware architecture. So it's really, I guess, a way to shield the user, us scientists, from these nitty-gritty details in the programming models. All right, what we also need to be concerned about is scaling, parallel scaling. We need to worry about the performance of climate models, and this is measured in simulated model years per wall clock day, and also want to see whether we have a path to exascale. Let's kind of take a look. And these are now diagrams, these are performance diagrams from DOE, and the first assessment they did was so-so. And what I mean by that, so let's take a look. We have a number of nodes on this axis. We have simulated years per day. This is one of the performance measures. How many climate model days, or years in this case, can you complete in one wall clock day? And we have a couple of lines. Let me get you through this. Blue and black are CPU codes, no GPU, yeah? And red our GPU codes. So, and you see a few of these systems here, Perlmutter, that's the NERSC system at DOE. We have Summit, that's the number 5 currently on the top 100 list. And then we had a prototype, which is a prototype of Frontier. This was pre-Frontier. This is hidden here in the red block. Okay, there are good things and bad things about that plot. What is good? Well, you only need very few processors to get really good performance with GPUs. Yeah? So the number of years you can simulate per day jumps by a factor of 8 to 10, probably, in this low regime. What's not so good, as you go to higher and higher node counts, the CPUs catch up on you. And that was a very disappointing result at first, because why would you spend all this time building GPU codes if you just could crank up the number of CPUs and you get the same bang for the buck? So what's your investment? And that was an unclear answer for this particular simulation. And let me point out, this is 100 kilometer grid spacing. This is coarse grid spacing. This is typical climate resolution. So for that coarse resolution, the answer is mixed. Yeah? So if you are only using a few nodes, yes, GPUs give you a good bang for the buck. If you have access to many, and you see the overlap here, you don't get anything from the GPU because there's too little work to do. Your problem, this is strong scaling, so your problem was split up into two little pieces. There's nothing to do for the GPUs. All right. Okay, but they didn't give up on that. And why? Well, that's not the only resolution we should be looking at, 100 kilometers. Remember, I told you the dream is 3 to 1. All right, and at 3 to 1 kilometer grid spacing, it's a completely different picture. Basically, without GPUs, you cannot do it at all. Yeah? Let's kind of take a look. Here are, again, two diagrams. This is from the DOE researchers. Here's Summit. Summit is currently number 5 in the top 500 list. So we have number of nodes here and now simulated years per day, but now we look at 3 kilometer and 1 kilometer in blue. Note that the 1 kilometer is measured in simulated days per day, not years per day. Yeah? But the amazing result, and look at the spread between the GPU result up here, this is on Summit, and then the CPU results, which are all down here. So on the GPU, you are getting an amazing, this is almost one simulated year per day. This is an amazing result on this machine, which, well, it's actually, maybe as a side note, this is using 100% of Summit. Yeah, so this is, of course, an allocation that's hard to get to come by. But at 100% of Summit, we are actually simulating a full year at a 3 kilometer resolution in one single wall clock day. This is amazing. And even more amazing now when you go to Frontier, and this is now a very hot off the press result just released a couple of weeks ago. When you go to the webpage, now on Frontier, this was their private allocation for 10 days. They went up here to like 8,100 nodes. And this is now in simulated days per wall clock day. So let's kind of take a look. In red, it's atmosphere only. In black, it's atmosphere, land, ice, and some ocean data. It's not quite a full ocean yet in the black line, but you kind of see two things. You see, yes, with atmosphere only, we are at an amazing over 1, and this is at 3.25 kilometer resolution. We are now over 1 simulated year per day. So this is 380 days on 8,000 nodes. And when you activate a little bit more complexity, meaning in the black line, complexity that comes in here through land, ice, and prescribed ocean, you're dropping a little bit. But this is now basically what they call a breakthrough. Yeah? So this is highlighted as a breakthrough for the climate sciences that we can do 1 year, simulated year per day on these machines. And bottom line, these are all, when you see, these are all in solid. Okay, you kind of see my, this is even having Summit and the Frontier system here together. So Frontier gives a little bit of an edge when you compare the solid lines versus the dashed lines. With CPU alone, there's no way we would ever get there. So that actually is an interesting observation at 1 kilometer or 3 kilometer, which brings up the question how we are doing this in general, not just at DOE, but in the community. And that brings up a topic which is called digital twins. I was invited to a panel just a few weeks ago, which was organized here by the National Academy of the Sciences. And we talked about digital twins for climate and weather modeling. And just to kind of give you a flavor of that discussion, which I thought was really an informing piece here in this conversation, just to give you a flavor, here's an atmospheric river. These are these really strong streams of moisture that hit typically the California coastline. You maybe heard about these in the news. They were hitting hard this winter. Yeah, we had a lot of rain here in California. This was a depiction of water vapor, accumulated water vapor in the vertical. And here's a simulation of that. This is coming from a NOAA, the National Weather Service model, of also not the same atmospheric river, but a depiction of an atmospheric river. So when I thought about digital twins, my immediate direction, yes, it's high resolution modeling. We want 1 kilometer, we want really good resolution and fine scale information. But when we then listened to all the other panelists, the surprising things was that there's absolutely no consensus what we mean by digital twin in the atmospheric sciences, and that may be even true in other fields. For me, it was always this. It was physics-based modeling, 1 kilometer or kilometer scale, and we would be in that category that I showed with the diamond runs. For others, we went to an extreme here. For others, it was full machine learning surrogates of the climate and weather system as a digital twin of planet Earth. And then for others, we were right in the middle where we are merging physical sciences and machine learning to do predictions. And it was really amazing to see that this disagreement, I guess, among scientists. I want to just highlight, and then I wrap up, a few things that we learned from NVIDIA, for example. NVIDIA presented at that Digital Twins workshop what they think a digital twin of planet Earth is. And their view is a full machine learning model. What I mean by that, they would train, they have data from observations, they will train a machine learning model, and then they use this to basically get a weather prediction. This is short-term, a weather prediction over just a couple of days, typically. The one thing I want to highlight with this, and this is a real good outcome for machine learning, that if you do that, the computational efficiency, of course, this is after training. So you train basically your machine learning model with hundreds you probably don't have, but like 50 years of 6-hourly data. Yeah, so a lot of data. And once you do that, then your query time to get a prediction for 2 weeks is only done under 1 second. So this is an amazing result. Of course, a normal weather prediction takes, well, a couple of hours at least on very big machines. Yeah. So this is one of their selling points. Of course, the speed up in comparison to numerical weather predictions is amazing, 10 to the power 4 or 5, and power savings are amazing. And this was kind of presented as the next thing, the next kid on the block, right? And if you then dig deeper, and this is now a cautionary note, just to kind of make you aware of the pros and cons of these ideas, and a cautionary note, when you then dig deeper, and dig deeper means there is this preprint you can grab, you will learn that, for some cyclones, this is now a depiction of a cyclone track, a hurricane track, here a couple of years ago. So this is an actual prediction of an actual hurricane with machine learning. I guess what we are seeing here in blue is truth. This is basically the observation, what they call observation, and in red it's kind of the machine learning prediction and an ensemble estimate here in the shading. Okay, that doesn't look too shabby, but then when it comes to strengths, and strength of a hurricane is typically measured as minimum sea level pressure, so the way they intensify, they did a super crappy job. Didn't really mention it that way, but then they kind of show this diagram. Here's the minimum sea level pressure. You kind of see the tropical cyclone. What they call truth is kind of going down, and the machine learning model is even not capturing that. And they sell this as an okay result. The truth is, it's a horrible result. Why? Because the actual observation, and I point this out here, was actually that this cyclone intensified to 920 hectopascal, and look at that scale, this is 985. So they actually missed the cyclone by 65 hectopascal. It's a huge, huge difference in strength. Why is that? Because they used training data that were biased. Yeah, so the machine learning training data, which is the blue curve, actually never had that cyclone, or couldn't these are basically cyclones in the training data that are never reaching that intensity. So just a cautionary note here. Okay. Okay, I want to wrap up with just a couple of comments. I guess this is a real quick walkthrough through some aspects of climate and weather modeling in the community. We also do a lot here in Michigan. So this is now a photo of my research group. A couple of people are even in the audience. And I would just want to maybe get the word out that we are contributing to all these efforts in the community. And what I mean by that, we are improving DOE's equation set currently for this 1 to 3 kilometer resolution. Yeah, you might be surprised to hear that, but still equations have their approximations. And we are now trying to even get rid of these to help them make an even better prediction in the equation set of the fluids code. We will be helping soon NCAR to take the GPU code from DOE, put it in the NCAR framework to enable them to do GPU modeling, which they can't right now. And a lot of laundry list here, other pieces, a coupling piece that we are contributing to. Okay, let me wrap up with just a couple of conclusions. And this is a long laundry list, as you see. I would just want to kind of point out a few key points. Well, current current systems, hardware systems are pretty much heterogeneous. What I mean by that, hybrid means they are distributed shared memory and they have the GPUs. So that immediately calls for GPU technology in the codes. But when you kind of look at the codes, and I kind of have this laundry list here, these models are at their crossroads. What I mean, the majority of climate and weather models are legacy codes in Fortran. The future probably isn't Fortran. The future is probably Julia, Python, C++, and others. So that's a big question mark here. C++ is already pushing ahead with DOE. What I also want to say, most codes are not GPU ready at all. I could only really show here DOE. DOE is the only real agency in the United States that has that capability. And they're also often hard to port to other architectures. And COCOS will be helpful to make this better, of course. The other scientific frontiers are actually more scientific questions. For example, I actually put it here. We need to really question our scientific assumptions in these code bases. So what worked for 100 kilometers does not work for 1. Yeah? So it's actually not just a cranking up of the resolution, it's a redesign of things we do. Yeah? So that's another frontier that we are looking at, and we do need support from software engineering experts. We as scientists are so poorly trained often in these new architectures that we can really enjoy that interaction with the software people. All right. The role of machine learning, and that's my last statement, the role of machine learning for weather and climate is up in the air. What I mean here, they may be usable, machine learning may be usable as surrogates for maybe time-consuming pieces of the code, maybe radiation, maybe a cloud estimation, and maybe that's doable. We don't know yet, and people are exploring this right now. It is highly debatable whether pure machine learning prediction will ever succeed in comparison to physical-based prediction systems. I really highly doubt that for climate projections. There's just not enough training data. We can't train for future climates because we haven't experienced and observed future climates. So we cannot use historic data to train. And this will be contested. And that should just ring the bell that machine learning can never extrapolate. And last statement, yes, there's a lot of exciting work to do. I guess let's get started, or even increase the pace, the speed at which we have been doing things. Thank you.
Thank you very much. Yeah, please go ahead. If you can go to a mic, then the recording would be good. Yeah, the mic is coming.
Thank you very much for a very nice overview. This may be a bit of a subjective question, but it's clear that the climate models are very important in trying to predict what we may expect for the future. But given the current uncertainty and then the number of variables involved, to what extent do you think climate models should be used to formulate mitigation policy? And at what point might that be a more direct correlation? Thank you.
Well, it's really the only tool we have to inform potentials or to inform us about potential outcomes, potential scenarios. So I think they're at a crucial, they're not 100% accurate. Don't know. We need to acknowledge uncertainty, and this is typically acknowledged in these big IPCC reports, big comparisons at the international level. But I think they are really the crucial tool to inform policymakers about potential outcomes.
Thank you.
So I'll just reserve, take a quick question, and then we move to the next speaker if you can get set up. Because there's also going to be a panel at 3, and there'll be more chances for discussion. But if the next,
Thank you for your talk. I was just curious, in your new model, if and how you model the ozone layer, and especially the entrapment of heat that it causes.
Excellent question. That depends a bit on the model design. We typically need chemistry modules, chemistry components in our models to do that, because ozone is actually a complicated product of some chemistry interactions, and that is done. Not in all models, I should say, but that is done at major centers. So there's active ozone chemistry, basically obeying the chemistry interactions.
Thank you.
thank you very much for
Sure, thank you.